So welcome everybody, and I guess I won't really talk about distance geometry, but I will talk about things that are quite related to it. And many of the players, I guess, that have appeared so far, they're going to reappear in this talk. So everything that I want to say is pretty much based on joint work with my student Diego, and I'll point out the appropriate references near the end. So what's the general context of this talk? It's really about trying to understand systems of polynomial equations, right? So imagine that you want to solve a system of equations, and somehow, of course, the idea is that this is a pretty large system of equations. And typically what will happen in many applications, including some of the examples I'm discussing in here, these are very structured systems of equations, right? Typically, when you look at applications like, a power network, like what we have over here, the structure of these equations very much correspond to the underlying structure of my power network, where in here my nodes, for instance, may be machines, and the edges in my graph in there may represent physical connections in there, and associated to this diagram of a power network, we can write an explicit system of nonlinear polynomial equations, for instance, that will describe the optimal operation of such a network. Right, another example is, for instance, given by, this is from the cover of this very nice book of Sommese and Wampler on how to solve systems of polynomial equations. And when you look at robotic manipulators, so for instance, this is a diagram of what's called a Stewart platform, then typically in there, again, you have, when you look at either the forward or the inverse kinematics, what you will have in there are essentially a system of polynomial equations that will relate the rigid bodies. Think about the robotic manipulator, and there's a certain structure in there which is given by the physical interconnection of the different degrees of freedom that I have. And typically, again, think about the example of your arm. It's not that my finger is connected both to my wrist, my elbow, and my shoulder. Typically, there's a certain graph in the way that things are connected to each other, and the equations that you write respect this topology. So the other example that we have in here, for instance, is come from mass action kinetics, from essentially the dynamical equations of a chemical system. The variables in here are these things in brackets. They represent concentrations of a different species. And as you can see, if I want to look at the steady state solutions of this, really what I have to solve is some system of equations. And again, typically the structure of those equations is not arbitrary. It's not that every variable is talking to every other variable, but typically what this represents is that I have two different species that will combine and produce something new. And you don't have typically 17 things that come together in order to produce something else. Typically what you have, perhaps many pairwise interactions that in the end are going to produce something different. So the point is really that, there's a lot of problems in many domains, and these are just an example. What one would like to solve polynomial equations. Typically those are large scale. If they're small, then it doesn't really matter. And in all these domains, structure is the name of the game, right? If you really want to be able to solve these kind of things efficiently, you have to spend some amount of time in terms of understanding the structure of these equations. So how we're going to describe these kind of things, how do people abstract, and I'll describe a little bit of the history of all of this. How do you abstract from the problem of solving polynomial equations to graphs? Somehow graphs are going to appear in here. So there's a very natural construction, which I'm going to describe in a second, that has appeared in a number of areas, that will allow us to go from a system of equations. It doesn't really matter at this point whether they're polynomial or not, but will allow us to go from a system of equations to a graph. And the construction is actually quite nice and quite simple. So imagine that I have in here a set of m equations in n variables. So my variables, I'm going to denote them from x0 to xn minus 1. And my equations in here are going to be these f sub i's. In my case, they're going to be polynomials, so for much of what I'll say at the beginning, at least, it doesn't really matter. And I'll have m of these equations, right? I have m equations in n variables. So what I'm going to do, I'm going to abstract out, or this construction proceeds by abstracting out from my equations in terms of a graph. So I'm going to throw out lots of information about what these equations are, and I'm just going to retain some combinatorial information that's going to tell me which variables are talking to which variables in a given equation. So in particular, the way that we're going to have in the graph, I'll show you an example in a second. I'm going to define a node, an undirected graph where the nodes are going to be my variables, x0 to xn minus 1. And what I'm going to do is for each equation, I'm going to add a click. A click is a complete graph that's going to connect all the variables that appear in that equation. Right? Here's an example. So let's imagine that I have this system of equations. And here I use, I guess, algebraic geometry notation in terms of just denoting the ideal. But what this really means is that this equation equal to 0, this equal to 0, this equal to 0, and this equal to 0. And what I'm going to do, as I said, I'm going to write in here, I have 4 variables, x0, x1, x2, and x3. So I'm going to draw 4 nodes over there. I'm going to look at the first equation, which are the variables that appear in here. I have 0, 1, and 2. So I'm going to draw a click connecting the nodes 0, 1, and 2. I'm going to go to the second equation. I'm going to draw a click. In this case, it's just an edge connecting variables 1 and 2. I already had that. The same thing for the third equation, and the same thing for the last equation over there. So what I've done is essentially abstracting my set of equations into a graph. And notice, of course, that in the process, I threw away lots of information. Right? I don't know anything about the degree of these equations. I don't know anything about the coefficients of this equation. I'm throwing away a lot of stuff, but hopefully this is telling me, for instance, that there's no equation where x0 and x3 appear together. Right? So natural question, I'll try to describe again where these kind of things appear. I mean, is this graph useful for something? Right? Does it help me in any way? If that graph is simple, does that imply anything? If that graph is complicated, what can we do? Right? And by the way, I mean, I'm very happy to take questions along the way. Right? So if something is not clear, please let me know. Good. So what have we done? In here, we've abstracted, as I said, this polynomial system into a graph. If you're fancy, instead of having a graph, you can write a hypergraph in there. You can retain more information that I've done than just kind of these clicks. You can annotate these clicks with further information. But again, let me do the simplest possible version. I just think of that graph that I have over there. Right, and natural questions, as I said, are, I don't know, does this graph, the structure of this graph, does it help me at all in solving my system of equations, like I said before? So for instance, I mean, even if you don't want to solve a system, I mean, we would have to discuss perhaps what do you actually mean by solving a system, right? I mean, do I want to solve this numerically? Do I want to obtain numerical values for the x's? Do I want, I mean, there's an algebraic notion of solving a system. Perhaps I want to compute what's called a Grosvenor basis. If you don't know what a Grosvenor basis is, it doesn't matter. The point is, for whatever your notion of solving a system is, we can ask, does this graph help for something? Perhaps I want to optimize over the solution set, and the question is, does this graph help me in any way? And in particular, a very important question in here, I mean, are there ways of preserving somehow the sparsity structure of this graph? Think about any of the examples that I talked about before. Think about the power network example. I may have, kind of 50,000 generators in the US. This graph is typically very sparse because you don't have a generator in California talking to one in Massachusetts directly. I mean, they may talk through other generators along the way. And kind of if somehow whatever method I use requires me to convert this very sparse graph into something extremely dense where everything is connected with everything, then perhaps that's a bad idea. Right? And of course, natural questions, I guess if you're more a CS person or optimization person, you would like to understand complexity aspects. I mean, again, this graph being easy somehow implies anything else. So these are not new questions by any means. I mean, they have been studied in 15 different areas, which I'll mention in just a second, over the past 40 years. And this notion of what's called graphical modeling or hypergraphical modeling, again, it's pervasive in areas such as numerical linear algebra. If you've ever taken a numerical linear algebra course, some of the notions I'm going to discuss are going to ring a bell. Statistical graphical models and machine learning, people are using this quite a lot. I mean, typically, if you want to describe a high-dimensional probability distribution, it's a huge object. So typically, you want to associate some kind of sparse structure to it, and sparse graphs is a nice object. Things like constraint satisfaction problems, in particular, or database theory, are areas where the kind of ideas that I'm going to discuss in here have been explored in quite some detail. And although kind of many of the things come from very different domains, either kind of computer science or mathematics or probability theory, there's been kind of a convergence around these notions of chordality and tree width. And part of what I want to explain during at least the first half of the talk is really what are these common notions and why they're so important in terms of understanding many of the things that are going on. So there's a lot of names. I mean, this is not a formal survey, but depending on which areas kind of you're coming from, you may hear all these different names associated to this set of ideas. So for instance, if you're a linear algebra person, the work of Blair and Peyton in sparse factorizations, I mean, they should ring a bell. If you're like a graph theorist, I mean, the work of Robertson and Seymour in graph minor theory, it's very related. If you're a logician, the work of Kurzweil in second order logic. I mean, there's a lot of kind of independent directions, and somehow this all somehow comes together in terms of these notions. And what I really want to explain again, is why these notions are so important. By the way, I mean, there's a lot of connections with things that we've seen already, and I'll try to point out those already. So for instance, in the talk that we saw yesterday in terms of these convex structures, I mean, one of the reasons why chordality is so important because it's one of the nicest examples of a kind of discrete generalization of convexity. In particular, an example, I guess you didn't mention explicitly, but it was kind of on the back of your talk, is, for instance, a nice family of convex subsets. I mean, generalized convex in the sense that he defined before are the subtrees of a tree, right? So whenever you have a tree and you look at subtrees of a tree, they have all the sparse, all the convexity properties that you would like, and those extend to the case of cliques on the chordal graph. And we'll talk about this a little bit later. So what's kind of interesting, at least for us, we were kind of interested in understanding how to solve polynomial equations, so there wasn't really work in computational algebraic geometry on how to solve polynomial equations that will exploit this structure. And at the beginning, we were kind of surprised, but kind of the more that we work on it, we realize that things are a little more complicated than somehow that this situation. And one of the other things that I want to explain is a little bit why this disparity and how can one can do something about it. And again, we'll see exactly how this appears. And I should also say that in discrete optimization, this is something that people have explored a little bit more on the continuous side, I guess it says, and there's some nice work, particularly on the semi-definite side, exactly the semi-definite completion result that Henry mentioned in terms of this completion of chordal graphs is going to appear or appears in semi-definite programming, and these are again some of the names associated to that kind of work. Okay, good. So I have a couple of definitions, not as many as I guess we have in the distance geometry world, but and actually some of those you've seen already. But actually, all the definitions that I'm going to have in here, we've seen them already during the conference, so let me just mention them anyway. So the first one is this notion of a perfect elimination ordering of a graph. I mean, I'm really going to be interested in chordal graphs. There's many, many different ways of defining when a graph is chordal, but in particular, the definition that I'm going to use is a one that uses a notion of a perfect elimination ordering. And I'll explain exactly what this is. There's other definitions of chordal graphs in terms of chords on 4 cycles and whatever, but this is really the one that we're going to focus. So what is a chordal graph? First of all, even before a chordal graph, let me define this notion of a perfect elimination ordering, which is some property that a graph may have or may not have. And the idea is that I'm going to say that a graph with vertices x0 to xn minus 1 has a perfect elimination ordering. So I have an ordering of the vertices x0, x1, xn minus 1. And I'm going to say that that ordering is a perfect elimination ordering if the following property is true. So think about the elements of my graph, the vertices of my graph. I'm going to start with vertex x0. And what I'm going to look is at x0 and all its neighbors. And if all the neighbors of x0 are neighbors of each other, then I'm going to proceed to the next vertex. So then I'm going to look at x1. I'm going to take x0 and I'm going to remove it. Then I'm going to look at x1 and I'm going to require it the same property, that all the neighbors of x1 in the remaining vertex, in the remaining graph, they have to be vertices. They have to be neighbors of each other. If that's true, I'm going to remove x1 and I'm going to keep going. Right? So yeah.
So it's in the future, not in
the future, yeah. So let me give this stupid analogy, but it's perhaps useful. So now if you talk to students about graphs, you have to say Facebook or or the French graph for stuff like this. So the story is that if you have all your nodes they're in a party, and people will start going to leave the party. So I'm going to have X0 that's going to leave the party. When X0 leaves, it will say bye-bye to their friends. And all their friends, they have to know each other. Right? And then X0 is going to leave. Then X1 is going to again leave the party. It's going to gather all their friends to say goodbye. And they all have to already be friends from each other. And kind of like this. Yes?
Excuse me, but when you are putting it, are you eliminating its neighbors? So if
yes, so this is exactly what I have in here, right? So I have what has to happen. I look at vertex L, and I look at all the vertices that are adjacent, but the ones that are in the future. So actually, nobody has used a board because I don't have a board. But let me just give a simple test example since we have time. I don't know how much you can see. I'll tell you what I'm going to draw. So for instance, if I have a graph like this is just a cycle, a 4th cycle. I'm just drawing a 4th cycle. Then it's clear that this graph does not have a perfect elimination ordering, right? Because certainly it doesn't matter which one I pick first. And if I pick this one of them, the two other ones are not going to be neighbors of each other, right? But for instance, if I change my graph, I added a diagonal, then that graph will certainly have a perfect elimination ordering because I can start with this vertex. The neighbors are going to be neighbors of each other, and I can keep going. But for instance, I could not start with this particular vertex. Right? It's OK. I will not use it.
I'm just testing for the next time that somebody wants to use it. All right, that's it. OK.
Oh, OK,
Next
good.
time, just wave and I'll do it.
OK, good. So again, it's a particular property that the graph may have or not, but it's going to be very important. We're going to see why. And actually, some of you, OK, let me define what a chordal graph is. A graph is going to be chordal if it has such a perfect elimination ordering. And that's an if. It's actually an if and only if. I'm using it in here as a definition. But if you define chordal graph in some other way, this is actually a theorem, right? That equivalently, every time that we say that that the graph is going to be chordal, there's going to be a certain way of ordering the vertices that it's going to be very convenient. And when I say very convenient, something, again, I said if you ever taken a course in linear algebra, you may know about the Cholesky factorization. For instance, one of the things that's very important when you do a Cholesky factorization is that the ordering of the variables matter. And the way that in linear algebra we know that this is true is because what will happen whenever you have a chordal graph is that whenever you do a Cholesky factorization in the right order, then what will happen is that there's no what's called additional fill-in. The sparsity pattern of a factor is exactly the sparsity pattern of the original matrix. So if you factor a very sparse matrix that in the right order for which a graph is chordal, when you factor it, then you're still going to get something that's very sparse. So this is a typical example. If you take a random 3 regular graph and you factor it in this is a Cholesky factor in an arbitrary order, you'll get something that's very dense. But if you pick the ordering very, very carefully, then you'll get something that's very sparse. Right, so. Good. So that's a notion of chordality. A graph is going to be chordal, again, if such an order exists. Of course, it's maybe a strong property, certainly a non-generic property. We have genericity a lot. So, but what do we do if you have a graph which is not chordal? We just add edges until it becomes chordal. And this is this notion of a chordal completion. So if you have an arbitrary graph like the 4th cycle that I had before, then what you're going to call a chordal completion essentially is a chordal graph with the same vertex set that contains all the edges of my original graph. I just added edges in some way until it becomes chordal. Right? And any such graph is going to be a chordal completion. In particular, there's always a trivial chordal completion, which is you just make it a clique. Right? You add edges until it becomes a clique. And that will certainly be a chordal completion. Of course, we would like to add as few edges as possible. So I told you there were 2 notions. One is chordality. The other one is tree width. Once we know what a chordal graph is, tree width is very easy. Because tree width of a graph is exactly the clique number, the size of the largest clique, of its smallest chordal completion. So what I do is I look at all possible chordal completions of this, and I look at the one that has the smallest, largest clique. Right? And again, the definitions are not easy to parse in real time. I'm awful at doing this when somebody else is giving a talk. So what I really want to tell you is somehow how we should think about tree width. And tree width is really a parameter. It's a number that you associate with the graph, that when you meet a graph and they tell you what their tree width is, you know where to put them on the spectrum of, kind of on the one hand, you have trees. On the other hand, you have the complete graph. So the idea in here is that every graph will have a number, like the slip number, if you want. It's a tree width. And if this tree width is equal to 1, then your graph is actually going to be a tree. If the tree width is equal to n, then your graph is going to be the complete graph. And if it has some number in between, it's going to be somewhere in between. So if it's, for instance, tree width equal to 2, it's not going to be a tree, but it's going to be tree-like in a very particular sense. And there's independent characterization, for instance, of these graphs. If you're a graph, if you like graphs, these are essentially what's called the series parallel graphs. I mean, it's a well-known family of graphs. But then there's everything in between. So for instance, if you look at the regular grid, the square grid, that's neither very much like a tree, nor it's very much like a complete graph. And it turns out if you compute it, the tree width is something like square root of n. Right? But it's a number that will tell you, kind of where your graph lies. Right? And there are ways of computing it and whatever. So, yeah.
So if it's chordal already, it's just a click number minus 1 or
yes. So chordal, when you have a chordal graph, kind of then the tree width is exactly the click number minus 1.
What chords would you add to number 2?
Which one?
Which chords would you add to number 2?
Oh, so this is a 5 cycle, so you can triangulate this.
Okay, but then you have a 3. Okay, 3, and then you take away 1. Okay.
Good. So why do we care about this? Kind of, or why I'm telling you that these notions are important. Again, I gave you a list of names. I told you that people have been doing this for 40 years. So let me resume, or let me summarize, kind of 40 years of research in one sentence, kind of, which is an awful thing to do. And it's really this meta theorem that says that every time that you have an NP-complete problem on a graph of small tree width, some graph that lives over here, then those problems are actually going to be easy. They're not going to be difficult. They're not going to be exponential time or anything like this. But actually, they're essentially going to be polynomial time. And I'm going to at least tell you the essence of why something like this is going to be true. Right? So this is, again, as every meta theorem, of course, there's all kinds of stars and disclaimers and things like this. But roughly, this is true. Kind of that whenever you look at your favorite NP-complete problem, and you have a graph which is easy in there, then kind of this, there's going to be a clever algorithm that's going to allow you to, non-trivial algorithm, that's going to actually allow you to solve this in polynomial time. If you want to read about these kind of things, this generality is something called parametrized complexity. You look at things as a function of some parameter. In this case, we're using tree width. I mean, there's a number of other graph parameters that you can use, but something like this is going to be true. So the first time that you see this is kind of a bit crazy. Kind of somehow it will tell you, I mean, roughly speaking, that if you want to solve, some stable set or max cut on graphs of tree width 10, regardless of the number of nodes, then kind of you're actually going to get some kind of polynomial time algorithm. I mean, let me just give an example to give a flavor of how this works. And this is, for instance, again, it's a very simple example. It's almost trivial, but kind of it's still interesting. Which is, for instance, what happens when you want to solve the stable set problem on trees. So let me describe what the stable set problem is. So this is, so we have a graph, an undirected graph. And then there's this notion of independent set or stable set, which is a subset of the vertices with the property that they're not neighbors of each other. Right? So for instance, in my 4 cycle that I had in there before I added the edge, I could pick 2 vertices in the opposite side of 2 opposite diagonals, and those are not neighbors of each other. So what's a stable set problem is computing a stable set of maximum cardinality. Right? Trying to compute the largest possible set of nodes that are not going to be neighbors of each other. It's kind of well known all the way from Gary and Johnson that kind of that problem is NP-hard. We cannot solve this problem efficiently on arbitrary graphs. By this meta theorem that I'm telling you before, I claim that for every family of graphs of bounded tree width, then there's going to be some algorithm that's going to solve this in polynomial time. right? Actually, even in linear time. And let me give, again, just a very, very simple example, which is, as I said, for general graphs, this is going to be NP-complete. But for instance, on trees, which is an extreme case in there, I claim that this is actually linear time solvable. It's not totally obvious, but let me show an algorithm that will do this. And it's kind of like a simple dynamic programming type recursion. So what I'm going to do, I'll explain this in just a second. But I'm going to write some kind of, first of all, I'm going to fix a root in my tree. And I'm going to, therefore, there's a unique path from my root to every leaf. And I claim that I can write the following recursion in here, where this function S sub I is going to represent the size of the largest independent set of the corresponding subtree. So I'm looking at the subtree. So if this is my root, I'm going to have the rest of my tree in here. I fix a node, and I'm just looking at the size of the independent tree from that node upwards. Right? And I claim that the following recursion is true. On the one hand, that if I just look at the leaf, then of course the largest independent set that I can pick is 1. Right? Yes, a leaf is cardinality 1. And I claim the following, that if you look at any other node, essentially you have two options. Either you take that node or you don't. If you don't take that node, then you can take all the children. So what you'll have is that this quantity is going to be the sum over the children of S of j. Or if you do take it, then you cannot take the children, but you can take the grandchildren. And that's kind of exactly this quantity over here. Again, it's a simple exercise. It's not complicated. The only point that I want to say is in this case we have a simple recursion that allows me to solve this problem by a recursion that will start from the leaf to the nodes. And this is really a form of dynamic programming. It's a little bit, it's a little bit distinct, if you want, from the traditional, it's really the same, but a little distinct from the typical way of doing dynamic programming, I guess, that we teach in many courses, because this is not just dynamic programming on a line, on a path, but it's actually dynamic programming on a tree. But it's kind of the same thing. Nothing changes much. Right? So this is for the case of trees. If you look at these graphs are more complicated, you'll have a more complicated recursion that's going to recur on clicks and whatever, but the details are somehow technical. The basic idea is really the same. You're going to write some kind of tree structure, and you're going to write some kind of recursion, and in the end, you'll get exactly the solution that you want. Right? This is more or less clear. Again, I don't care about the specifics of the algorithm. The only thing that I'm doing in here is illustrating this meta theorem. I have an NP-hard problem. If I were to do this on arbitrary graphs, I'm lost. I don't have a way of solving this in polynomial time. But because I'm looking at graphs of a very particular structure, then in this case we have an algorithm. Yes?
So is the meta theorem backwards for largest clique?
What do you mean?
Largest clique.
Yeah. For the largest clique, the same thing is true.
It's backwards, right? Because it's the same problem in the other direction. You want very dense graphs to be easy.
Well, so necessarily, yeah, but there's an implicit trade-off in here, right? For a graph to have small tree width, it has to be kind of sparse, right? So in particular, you're always bounding the size of the largest clique in here, right? The tree width is going to be a bound on the size of the largest clique.
Okay.
Yeah. And you can actually find the largest clique in this one.
But isn't largest stable set the same as largest clique problem on the anti-graph?
On the complement, yeah.
So it's easy on dense. So if your first problem is easy on sparse graphs, your second problem is easy on dense graphs.
No, because doesn't depend. Tree width does not depend just on sparsity. You can have
I meant tree width. If stable set's easy with small tree width, then largest clique is easy
on
high tree.
But the tree width of the complement is not the that's not.
Oh, tree width of complement is not n minus.
Right. Yeah, exactly.
Isn't something like the meta theorem a theorem with for perfect graphs?
Well, for perfect graphs, it doesn't really matter. It's not about tree width. So when you look at perfect graphs,
Chordal graphs are perfect. Right?
Chordal graphs are perfect, but there's lots of families of perfect graphs that don't have bounded tree width. Right. So that's, in a sense, a stronger theorem.
Yeah.
Right? And that's specific to the case of independent set. In here, it's pretty much kind of any NP-hard problem.
It's true for any hereditary property. I think it's a theorem of Roberts and Seymour that for perfect graphs, you take any hereditary.
There's much more powerful, there's much more powerful results. Yeah. Let me not, yeah. Yes?
Is this really any NP-complete problem, or
There's all kinds of stars, and we're going to see
it's
exactly
a
what
general
happens.
algorithm?
The general algorithm is essentially dynamic programming. I mean, more sophisticated versions of dynamic programming, but somehow there is a meta theorem or meta algorithm also, which is, let me give a concrete version. You construct something called a click tree, and then you do kind of dynamic programming on the click tree. Yeah.
The point is that in the dynamic program, you have a finite state space if the tree width is bounded. That's all you need. So if you bound tree by constant, it gives you a constant size state space. Like at the square root of n, it wouldn't work. And then anything you can encode that NP property in first order logic, for example, you can do this way.
Yeah, we're going to see actually exactly how that appears later. It's kind of interesting. Okay, good. So, I gave you this example, and kind of up to this point, we were so happy. I mean, kind of once you read about this, like Amirali, kind of now you get very excited. You think that you can turn this into kind of very much any problem that you would like to solve. But then you start playing a little bit with this, and you realize the following. Okay, let me look at perhaps something like the partition problem, right? I mean, we heard the partition problem earlier also, I guess, earlier today. So the partition problem, again, many of you know this. I have a set of integers, and what I'm trying to say is, can I split this set of integers into subsets in such a way that the sum of those ones is the same? And many of you know this kind of standard way of writing the partition problem. Just you assign variables plus minus 1, that will say whether you're in one subset or the other, and then you write the coupling equations. But let me write a different formulation of that. Because if you write that formulation, then the associated graph is going to be a click, and you're not going to, a complete click, and you're not going to get anything interesting. But let me write it in the following way, where now my variables s sub I are going to denote the partial sums of my variables. So I'm going to do the running sum of my variables, of my a sub i's. And I can write the following system of equations. What is a system of equations? Something very simple. S0 is equal to 0. If I don't add any variable, I set it equal to 0. And then what happens? Then either I put variable a sub I in one set or the other set. I either add it or subtract it from my running sum. So that means that a sub I is s sub I minus 1 plus or minus a sub I. Right? Just a system of equations. And I know, and I want that Sn, the final sum, is equal to 0. I claim, this is a very easy claim, that this system of equations is going to have a solution if and only if kind of my subset sum problem has a solution. Right? And something very interesting or very frustrating will happen in here, that if you look at this system of equations and you do exactly what I told you before that you're supposed to do, look at the system of equations and write a graph. The graph that you'll obtain is a tree. It's actually a path. Tree width is going to be equal to 1 because it's a tree. And kind of you'll say, yay, I have a polynomial time algorithm. But on the other hand, it's kind of well known that kind of this was NP-complete. I mean, that partition is NP-complete. So somehow there's something that's wrong somewhere, right? Kind of I have in here a nice NP-hard problem, kind of, and kind of I write it as a polynomial system of a tree, right? So I'm lying somewhere, perhaps. So, but also, kind of what you can think, again, let's put aside this for a second, perhaps this is some bug in the matrix, kind of, and then you say, okay, let me ignore this, let me kind of go back to my, I'll solve that question in just a second. But let me point out also some other possible source of bad news for solving equations, which is kind of the following, right? So one of the things that we know, again, from linear algebra, is that these good elimination orderings, they preserve the graph structure. I mean, that's very much a reason why they were developed in linear algebra. I mean, they're perfect, right? When you do it, as I said, the Cholesky factorization of a sparse matrix, the factor is also sparse. So if you have 1 million variables, but the graph is very sparse, all your computations are going to be sparse. But when you look at polynomial equations, things are more complicated than linear equations, as you would expect. Right? So for instance, if you have a system of equations like this, right? So these are very simple equations. x0, x2 is equal to 1, x1, x2 is equal to 1. And if you look at the graph associated to this is again a path. Again, there's many notions of what does it mean to solve these equations. One notion which is very important for a number of reasons is the notion of a Grobner basis. I will not define what the Grobner basis is. It doesn't really matter for this talk. But the point is when you look at every possible Grobner basis, every possible notion of solving this system, what's going to happen is that there's going to appear, in the process of solving it, there are going to appear polynomials that combine x0 and x1. So the structure of my graph is going to be destroyed. If you input, again, this is a toy example, but think about any of the examples I talked about before. If you input something like this to your nonlinear solver, algebraic solver, there's going to be polynomials in there that are going to combine x0 and x1 directly. They're going to talk to each other. And the problem is that even if you input kind of like a perfectly sparse graph, and I'll show you some examples later, you may end up with kind of like a horrible mess of where every variable is talking to every other variable. So somehow, natural question is some kind of alternative descriptions, alternative notions of solving something like this that will play nicely with the graphical structure. And these two problems, in a sense, are coupled. We're going to try to understand what went wrong in the example before and kind of what's going wrong in here and what are possible ways of solving this. But what should be hopefully, you should be fighting with is, kind of what's the contradiction? What went wrong in there? On the one hand, I told you 40 years of research told you that trees are good and you can do everything nice on trees. And on the other hand, I gave a simple example where trees are empty hard.
Well, maybe the paths are bad and the trees are good. You showed us paths.
That'd be like a failure of logic. Kind of, and if that was true, then there would, that'd be bad, indeed. But that's not what's happening. Yeah. So really where things go bad really have to do with, remember that the algorithm, the way I described, or the reason why these kind of algorithms work really have to do with dynamic programming. Right? And something funny goes on when you look at what's really happening with dynamic programming, that there's like two elements that have to be true kind of for this kind of methods to work. One really has to do with, as I said, really the reason both why that meta theorem is correct and why that meta theorem fails in these kind of examples really has to do with dynamic programming. I mean, that's the reason why those theorems work. And there's a lot of refined cousins, more sophisticated versions of dynamic programming. Again, if you're an optimization person, you may have heard about things like non-serial dynamic programming. If you're a machine learning person, people talk about belief propagation. But these are kind of really all the same things. Right? And somehow what goes on in there really has to do that there's really two elements that you need to, that they have to be true in order for you to be able to solve a problem using dynamic programming. On the one hand, you need some kind of nice combinatorial structure, exactly the kind of graphical structure that we have in there that actually allows dynamic programming to work in principle. But the other property, which is quite important and it's somehow easy to ignore in the continuous case, is that you really need to control in some way the complexity of the objects that dynamic programming is propagating. And I'll try to make this clear in just a second. Somehow if you don't have a way, so dynamic programming gives us a recursion, like the recursion that I wrote before for this function SY. But if that object, as you propagate it, it grows more and more complex, then kind of just because you have some finite object in which you have to propagate your kind of your function or of your object, kind of if you don't have a way of bounding that complexity, then things are not going to work. And it will become clear again in the case of what we talked about earlier. So let me mention perhaps a few analogies. I think some of you may come from different areas. But if you know, for instance, anything about like optimal control, essentially dynamic optimization, then we have exactly the same question, right? Kind of when you write an optimal control problem for somehow nice objective functions and nice dynamics. So if you pick your dynamics to be linear, for instance, and your objective function to be quadratic, what happens is when you write the dynamic programming equation, you start with a quadratic function, and when you propagate it using dynamic programming, it will always remain quadratic as you propagate it. Because something very special happens for quadratic functions, that when you have a quadratic function in many variables, and you do partial minimization on a set of variables, the result is again a quadratic function. So think about the case I have a quadratic function in x and y, and a convex quadratic function in x and y, and I minimize it with respect to y. So what will happen in that case is that the result is actually a quadratic function of x again. The same thing happens in probability. When you do filtering, for instance, or statistical inference, think about the Kalman filter, you have a Gaussian distribution. And Gaussians have the beautiful property that whenever you condition a Gaussian or you marginalize a Gaussian, then again you obtain a Gaussian. But if you have an arbitrary distribution, and you either condition or you marginalize, unless you're very lucky, typically there's no bounded class in which this object remains. And you have to somehow propagate arbitrary probability distributions, and there's no finite dimensional description of those ones in general. And very much the same thing is going to be true in here. Unless we're in very particular situations, and I'll give a geometric interpretation of these nice situations, as you propagate these objects, they will grow more and more complex. And they will not be somehow any kind of way of describing this in some kind of bounded space or kind of with bounded resources. And I'll give examples in just a second. Again, what is the key of this? That every time that somebody tells you you can solve this using dynamic programming, there's really two parts. One is the dynamic recursion itself that will tell you kind of what you're propagating. And then you have to ensure that kind of the object that you're propagating can be described always in some kind of concise way. And we'll see exactly what it failed in the example that I told you earlier. By the way, I should have mentioned, I guess I had it in here, but I didn't. I saved it too quickly, that of course this problem is exactly the one-dimensional realizability problem of cycles, right? We heard this also in the talk this morning, right? So if you only care about distance geometry, then kind of that's kind of good.
Not equivalent, right?
It's essentially equivalent. I mean, it's really the same problem, right? A one-dimensional cycle is realizable.
Oh, the cycle, yeah.
Yeah, cycle. Yeah. I mean, it's a easy part in this paper, right? The hard part is the strong empty hardness. Okay, good. Okay, so how do we get around this? And in particular, why that meta theorem was somehow still true in some sense, and why it's not true for kind of my example. And really, again, there's a number of ways of interpreting what's happening. I really like geometric interpretations, and really has to do with some kind of geometry of the feasible set. And it's actually quite interesting condition from the algebraic geometric viewpoint. I hope you don't get offended by my cartoon. But kind of the idea in here is that there's a very natural condition that has to do with the degree of the projection into the Clique subspace. And that's a mouthful, so I'll just show a picture that I think represents exactly what I want to say, and it's kind of the following. Right, so let me go back to my example that I had before. So think about my example for a graph kind of in there, where I had this free clique and this edge over here. And what I'm going to do is kind of try to understand the following, right? So what I'm having here, what is a red curve in there, is a full solution set of my equations, right? So I have my set of equations, these equations I want to solve, and they will have some solution set. If it has a finite number of solutions, this may be a cloud of points. If it's kind of some curve or some variety of high degree, it may be some funny object like the one that I'm here. And the point is, I don't want to talk about this object directly, because this object lives in a very high dimensional space. Right, again, think about the case of a graph with 1 million nodes. I don't want to even think about this variety in this 1 million dimensional space, but I really want to think only on the things that I can access easily, which are somehow the cliques. Because the cliques are going to be small if the tree width is small. So I'm going to look, instead of looking at this, I'm going to look at the projections of this onto the subspaces spanned by the variables in the maximal cliques. So for instance, in here, I'm going to look at the subspace spanned, again, this is just a cartoon. So imagine I'm looking at the subspace spanned by x0, x1, and x2. So in here, this is a space R4. In here, I have x0, x1, x2. So I look at the projection of this on the span of x0, x1, and x2, this clique. And I look at the projection of this on the span of x2 and x3, which is the other clique. And the idea in here is that even though this is million-dimensional space, if the maximum size of a clique is 5, now what I'm going to have is lots and lots of 5-dimensional projections in there. And what I want to try to do is somehow glue all of these together, perhaps, and try to see if there's a global object in there, that somehow agrees with all of those ones. So what is a condition somehow that's going to appear in here that we're going to require? We're going to require that the projections that we have in here, they will have to have bounded degree. So if there's a cloud of points, then I have to require in here that somehow I don't have too many points in the projection. Or in my case, if I have some curve in there, I have to require that the curves, the projection in here, which is going to be some kind of curve in there, some kind of algebraic variety in here, this algebraic variety will have low degree. Right? And somehow this is a condition that we need. It's not a condition about this object, but it's really about the condition on the projections. That these projections, they have to be somehow easy to describe. They have to be amenable. And now we can see exactly why, for instance, in the discrete case, or in certain cases, which is a setup of all the theorems that we had before, somehow this condition is automatically satisfied. Because, for instance, many of these papers that I was talking about before, they could look, for instance, at the 0-1 case. So they could look at combinatorial optimization problems where my variables are constrained to be 0-1. So what that would mean is that this variety in here, my red variety, is really going to be like a subset of the vertex of the hypercube. So what I have in here is just some vertex of the hypercube in dimension million. Right? So I have the hypercube in dimension million, and I have a perhaps very, very large set of vertices in there. But notice that something very, very particular happens when you take a hypercube and you project it in the coordinate direction. Because what happens is that all these points are going to lie on top of each other, and what you're going to have in here is a small dimensional hypercube. Right? Even though in here I may have a hypercube in dimension 1,000,000, if I project on a 5-dimensional space, I marginalize on a 5-dimensional space, at most what I'll see 32 points. I will not see anything more than that. All the other ones are going to lie on top of each other. And the same thing is going to be true on every projection. So even though in here, this variety may have astronomical degree, all these projections are themselves going to be small. And because of chordality, it turns out there's going to be a nice way of assembling all these projections together in a way to reconstruct this object. What's very interesting, and this is really the difference between what we're doing and what people were doing before, somehow lots of the work before really had to do with this. But once you start thinking of this in this algebraic sense, then you realize that you don't really need this to be discrete. Like in my example, or in my cartoon, in here, if in here you have just an algebraic variety, as long as the projections have low degree, then the same kind of situation is going to be true. And a very interesting example, a very interesting family of examples where this happens, is where this is what's called a determinantal variety. Think about matrices of low rank. That's the simplest example. If I have in here a matrix of 1,000,000 by 1,000,000 that has low rank, and I look at any submatrix, the submatrix is also going to be low rank, and therefore it's going to have low degree. So again, this variety in here, the degree is going to be huge. Even if you look at rank 1 matrices of size 1,000,000 by 1,000,000, the degree is incredibly high. But the projections in here, they're going to have low degree. And we're going to be able to bound nicely the degree in terms of the size of the maximal cliques. So this is really the picture that underlies everything that I'm going to say later. That as long as we can control the complexity of these varieties, then somehow this idea of combining dynamic programming with this reconstruction, it will work, and will completely generalize all the things that we can do in discrete domains.
The question is by degree, you mean degree of a single polynomial that is?
I mean, no. So when you have an algebraic variety, there's a notion of the degree of the variety. What does it mean? Think about in the case of curves, like I have in here, what do? You intersect this with a random line, and you count how many points you have. And when I say a random line, you're going to count the intersections over the complex numbers. And there's a number which will not depend on which line you pick. It's a generic property if you want on a variety. If I take a random line in any direction, the number of intersections over the complex numbers is going to be a fixed number. And that number is going to be exactly the degree of the variety.
This number can go up or down on the projection?
So, I mean, once I project, I have a variety, and there's a number associated to this. Oh, yeah. I mean, so think about the case. The simplest case is to think about the case of points. If my variety is just a union of points. The degree is really how many points I have. And in that case, depending on the configuration of these points, if I pick a random cloud of points, of course, when I project them, I'll have exactly the same number. So the degree is going to be the same. But if my points are carefully aligned, like the vertices of the hypercube, whenever I project them, the number may go down exponentially or something. Good. So this is really the picture, and the question is, what can we do with this? The point is really we're going to be able to do a number of things. I guess I'll just show you. So the kind of things that we can do is, on the one hand, I want to really describe two basic ideas. One has to do with somehow an algorithm that will solve polynomial systems preserving this kind of structure with the notion of something we call chordal elimination. And it's a very nice idea that generalizes something that people have done in database theory, and I'll try to explain the connections. And the other one is some very, very nice data structure that Diego came up with, something called chordal networks. And it also will generalize some very, very interesting data structures that are coming from computer science, something called binary decision diagrams. So what is the idea again? What am I going to try to do? I'm going to try to give a way of solving a system of equations whenever they have this structure. And what I really want to do, again, keep in mind this example of I have a system with 1 million variables, and I never want to do computations with 1 million variables at a time. Right now. But perhaps my system has a maximal, has a chordal graph, or it has some kind of tree width bounded by 5 or 10, and somehow I want to be able to do computations only with a small subset of variables at a time. So what's the idea? I'll give an example in just a second, but let me describe at least a high-level version. But the idea is that what we're going to do is a way of eliminating variables. In algebraic geometric terms, this means that you're going to compute some kind of decreasing sequence of ideals. These are what's called the elimination ideals. But the basic idea, not ideals, the basic idea in here is going to be kind of the following. I'm going to have my equations. I'll show an example in just a second. But again, what am I going to do? I'm going to look at, remember, I start with my equations. From my equations, I will construct a graph. From the graph, I'm going to construct a chordal completion. And for the chordal completion, I'm going to get a perfect elimination ordering. And I'm going to use that ordering throughout my algorithm. So what am I going to do? I'm going to look at my ideal, that means the current equations that I have, and I'm going to split the generators in one set, in two sets. This set is going to contain my variable and all the neighbors, my current variable and all the neighbors, and all the polynomials that contain only my variables and the neighbors, and this is going to contain everything else. And what I'm going to do is I'm doing computations only on this part. I'm going to eliminate the variable that's going to leave the party. And then I'm going to put the equations together, and I'm going to continue the process. I'll show an example in just a second. Right, so ideally, what we should obtain is kind of somehow exactly what's called the elimination ideal, exactly the projection on this set. And the only things that I want you to notice is that exactly because of the properties of a perfect elimination ordering, this graph structure is going to be preserved. Because in here, remember that when I look at my variable and all the neighbors, they're already talking to each other. So whenever I do this elimination, somehow I'm only computing in a ring. I'm only computing with exactly the number of variables that correspond to the size of that clique. I'm not using all the variables at all. An example will make this clear. But the 2 points that I really want you to notice is that by chordality, the structure is always preserved. And as I do things, I always compute in small rings. I never compute with 1 million variables at a time. Right, so here's an example. Hopefully this will make it clear. So I have in here my system of equations. Right? Again, if I go from this to the graph, I'll obtain this nice graph over here. A perfect elimination ordering for this graph is 0, 1, 2, 3. So I have over here. So what am I going to do? This is my set of equations, and I'm going to partition them in two, right? I want to eliminate variable x0. So I'm going to look at the clique associated to x0, so it's 0 and 2. So in here, I'm going to put all the polynomials that contain the variables 0 and 2. And in here, I'm going to put all the other polynomials. And now I'm going to eliminate from this set variable x0. And there's good methods for doing this, essentially, standard. Right? Even by hand, I guess you can do this. If you eliminate from these two equations variable x0, what you'll get is this equation over here. These two equations, they go over there, and I play the same game. Now I'm going to try to eliminate the next variable that I want to eliminate is x1. So in here, I'm going to put all the equations that contain x1 and its neighbors. So all the equations that contains x1 and x2. And again, I eliminate x1 from here, and you obtain this term over here. I add this equation over there. Now from here, I eliminate x2, and I get this equation. And what will happen if everything goes well? So far, I haven't checked any condition, but if everything goes well, what should happen is that this system of equations is now triangular, and I can solve my system just by solving backwards. So essentially, I would look in here, I solve for x3, then giving x3, I solve this for x2, and then I solve this, and solve like this. Right? And what I want you to know, this is a part that's really important, that when I did this, I never computed with 4 variables at a time. I only looked at operations, these elimination operations were always on sets that contained at most 2 variables. There were different pairs of variables in here. But I never computed with more than 2 variables at a time. And why 2? Because the size of the largest clique in this graph is equal to 2. Right? Is that clear? Somehow the mechanics of it. Now, you may think, OK, what are you doing? I mean, you can always do this. But that's false, right? You cannot always do this. Because if the condition that I gave before fails, then you'll get the wrong results. So for this example, for instance, again, the structure of the equations are different, but the structure of the graph is exactly the same. So if you follow the process in exactly the way that I told you before, you'll go from here to here to here to here. I mean, the problem is not the 0. 0 is fine. This would mean that the value of x3 is arbitrary. But the problem in here is that this will give you the wrong solutions. So this should tell you that you can pick x3 arbitrarily, which is fine. This will tell you that you can pick x2 equal, you have to pick x2 equal to 0. But the problem then is that if you pick x2 equal to 0, then you're going to be stuck in here, because you cannot solve for x0. Right? So somehow this example that I have in here is bad. This example that I have in here is actually good. So this will fail. This will satisfy the condition that I had before. This will actually fail the condition that I had before. And it's certainly non-obvious why in one case it will work and in the other case it will not work. So what do we do in the paper? And I'll perhaps highlight this very clearly. We have conditions that are testable for my system that will actually guarantee that this choral elimination, this process actually succeeds and it computes the right thing. Right? So by the way, good test. What goes wrong? Remember, for the path example, for the knapsack example, or the partition example that I described before. In there, of course, you can do this process. But what's going to happen is that as you eliminate variables, the ideals, I mean, the set of equations that you're going to be obtaining, they're going to grow more and more complicated as you pass them along. Why? Because you're going to have lots and lots of roots. There's going to have lots and lots of equations, lots and lots of solutions, and you won't be able to, even though you know that this will at most take n steps, we will not be able to bound the complexity of the intermediate results that are going to appear along the way. And it turns out that in situations we can, again, let me at least flash the kind of conditions in there. But essentially, as I said, we need conditions for this to work. This example that I showed you before, or this couple of examples, show that unless you do something, it may get the right result or it may get the wrong results. And there are conditions. Again, they're not important, I think, for the purpose of this. You can read them in the paper. But a simple set of conditions, for instance, if you can guarantee that certain ideals that appear along the way, there is zero dimension, they only have finitely many solutions. What's nice about, I mean, even though this is a simple case, what's nice about this is that this contains all the situations of finite fields and 0, 1 cases, which are essentially all the results that I told you before, right? But what's interesting is that there's versions of this, I mean, generalizations of this result, that will actually ensure that this process works even though you don't have finitely many solutions. And again, let me not describe the details of what these conditions are, but there are some conditions on the structure of my equations. If my equations somehow they're nice in the technical sense, and this process is actually going to work, even though I don't have finitely many solutions.
20 minutes.
Yeah. And what's intuition, if you want? I mean, really, I guess I talked a little bit about this, that this variety will have small coordinate projections. We can compute independently all these projections in the maximal clicks, and because of chordality, we can actually glue the solutions in a consistent way and produce a solution in the red object of stars. So that's kind of there. Again, is the idea somehow clear? The really important part, or at least what I really want to stress, is that provided the right conditions are satisfied, we can solve these systems without ever somehow considering all the variables at a time. I can look at different subsets at different points, and and eventually I'll compute the right thing. And there's results that, well, I mean, if you look at the paper, that things will happen in polynomial time and blah blah blah. That's technicalities. Okay, good. So the other thing that I want to discuss, I guess, in the 19 minutes I have remaining, is to go back to this question that I mentioned, that perhaps we want, I mean, this is nice, it allows me a notion of solving, but quite often I want to do a lot more. Perhaps I want to do things like, optimize a function, or I want to do something called ideal membership, which I'll describe in just a second. I want to have a nicer way of describing the solution set. And let me somehow, that will preserve, again, the structure of my graph as I go along. And let me describe this with an example, right? This is a very nice example. I guess it goes back to, this formulation to the thesis of Dave Bayer. That has to do with, for instance, looking at colorings of a graph. I mean, John wrote a very nice paper with Jesus and Matthias. I think Matthias was there too. Not Matthias, with Jesus and Susan, I guess, on trying to understand solutions of these equations. But let me, for instance, look at the three colorings of this graph, right? So what I'm going to do in here, so I have the graph with, I guess, 9 vertices in there, and I'm going to look at the set of all possible three colorings of the graph, right? So it's kind of nice that there's a very nice formulation of all the three colorings of my graph in terms of a system of polynomial equations. What is a system of equations doing? Something very simple. So essentially, instead of coloring with coloring with colors, I color them with roots of unity, right? So I will assign to each node a cube root of unity. So essentially, the solutions of this are telling me that I assign to vertex I one of the three roots of unity. And then I can write a compatibility condition that's telling me that whenever I have two variables x sub y and x sub j along an edge, that they have to be different. And if you write down what that means, this polynomial vanishing means exactly that I assign different colors in there. So these equations exactly encode all the proper three colorings of the graph. If you count the number of solutions of that, should be exactly the number of colorings in this graph. And one of the things I want you to know is, of course, that coloring the cycle graph should be very easy. Any first year kind of MIT student can kind of color a 3-cycle graph. But if we go to your kind of your favorite computer algebra software and you ask to solve this system of equations, say computing Grobner basis, it will tell you something like this. You try to compute a Grobner basis, it will return lots of polynomials. If I pick one at random, it will give me, for instance, this horrible object in there. And this is somewhat disturbing. It's certainly disturbing to us. There's reasons why somehow, and actually in John's paper, one can understand a little bit why these things happen. But in particular, it should be a little bit frustrating that kind of somehow I would not be able to write this by hand, but kind of somehow I would know how to color this. So somehow, even though this is giving me this and all the other polynomials are giving me a description of the feasible set, a description of all the colorings, is not a description that somehow preserves the structure of my graph. Like I said before, right? Like, in there, any variable is only talking to its neighbor. When I look in here, there's all kind of crazy stuff, right? Like, kind of like this, 4 variables talking to each other. I have squares in there. It's not very interpretable, right? What exactly is happening in here. And I claim, and we're going to formalize this in just a second, that there's a nicer description, at least for this example, we'll see how it generalizes, of all the possible colorings of this graph. And let me describe in terms of the following data structure. This is really a data structure, which is going to do the following. What am I going to do? I'm going to really write this representation in here where there's a whole bunch of polynomials, ignore what they are. What's kind of interesting about this data structure is that somehow it's organized in the structure of a path in this particular case. So I have a path over there, and I have in here, somehow if you shrink all the blue nodes in there, I really have a path just like this ones. I have arrows that go from the top to the bottom only. And one thing that's going to happen, one can see perhaps easily, that I can read out from this data structure all the possible colorings of my graph very much by starting at the bottom and kind of going upwards. And this will mirror exactly the process that you would do by hand of coloring a graph, right? I can pick a color arbitrarily for variable 8. Then subject to this condition, I can pick a coloring for variable 7, then for variable 6, and there's 2 possibilities. Either I pick the same as 8 or I pick a different color, and then I can follow all the process. And what happens, it's a non-trivial property of this, that any path in here that you follow will actually give me a solution, and there's going to be an exact bijection between the number of paths in here and all the solutions of my polynomial system. Right? And there's one fact which is kind of interesting. This is really the reason why this is very interesting, because the number of colorings I will have in there is actually exponential. If you compute it, it's a Fibonacci number, that doesn't really matter. The point is that this grows exponentially with the length of the cycle, but the description of this object that I'm writing in here is polynomial. Clearly I can write this for any n. I just have to make this variable taller. So what we want to try to understand is, okay, perhaps something very, very special is happening in this case, but to what extent can we do this for an arbitrary system? Right? This is really what we're trying to understand. So it turns out that we can do this. This is your first example, if you want, of something that we call the chordal network, which is going to be a very interesting object. And it's really a new representation of the solution set of a structured polynomial system. It doesn't apply in general. It will apply in this low tree width situation. And rather than writing a definition, I'll write a definition in just a second. Let me tell you the features, the basic features that are going to appear in here. And it's really a little bit what we see in here. The 0th order feature is that if you look this from far away, in this case it looks like a path. In general, this will look like a tree, and I'll flash an example in just a second. But also, and what's very important, is that it will give a very, very clever encoding of all the solutions in terms of subcomponents, either paths or subtrees of this particular graph, of this particular network. There's going to be a way of encoding or reusing exponentially many objects in terms of kind of some small diagram. And I'll give an examples and I'll show why that's useful. It turns out that we can compute it. There's going to be a nice algorithm to compute these chordal networks. I'll just flash it and describe it. And what's very interesting is that a lot of interesting polynomial systems, like these coloring examples in there, they will actually admit small chordal networks, even though the number of components may be exponentially large, exactly like in the coloring example. We have, if I were to explicitly write down all the colorings, kind of I have an exponentially large list, but I can write this very compact data structure that contains all the solutions in a way that I can query in some kind of efficient way. And not just query, we're going to see that I can solve lots of questions about this. If I want to count solutions, I want to compute dimension, I want to solve the feasibility question, radical membership, elimination, lots of the kind of things that one would like to do with polynomial systems, you can do that effectively once you have a nice chordal structure. So I'll again highlight perhaps each one of these points, and I'll show some examples, and we'll finish. And that will be in less than 10 minutes. Good. So I showed you one example in here. This is perhaps very nice and very symmetric. Let me give a more complicated example, but I need to define something a little bit before. Again, I won't define it formally. It's really just a consequence of this notion of an elimination ordering. Once you have a perfect elimination ordering, and again, this also comes from the linear algebra literature, there's this notion of elimination tree. If you're an expert in Cholesky factorizations, you remember about this perhaps you remember about these elimination trees that you do for graphs. And what's this elimination tree? Something very simple. So remember, I gave this example of people coming to the party and leaving the party. So it's just a directed tree that points from, from you to which one of your friends left the party immediately after you. So for instance, in here, the blue graph is my starting graph. I want to do a chordal completion. I will have to add the green edges in there. The numbers in there indicate a possible elimination ordering. And what happens in here, kind of what we, as vertices start leaving, 0, 1, 2, 3, 4, whatever. What we have in here is we draw an arrow from the current node to the next friend that's going to leave the party. And it turns out this is a tree. We can root this tree in the last node, and this will give kind of some tree. Again, details are not terribly important. If you give me a perfect elimination ordering, you can write a directed tree, and this directed tree has lots of nice properties. Why do I say this? Because now I can tell you, at least, again, from 10 feet away, what a chordal network is going to look like. Let me show an example, and then I'll come back to the definition. But really, a chordal network is going to look a little bit like this. If this object in here is the elimination tree that I described before, notice it's skinnier, but this tree is exactly the one that we have in here. So what a chordal network is going to look like, the structure of this, again, from far away, is going to be exactly the same. The nodes in there, now they're going to be polynomial sets. So in here, I have a set of polynomials. In here, node 6, I have a set of polynomials. In here, I have a set of polynomials. And there's arrows between them. And these arrows, again, they always go from something higher in the tree to something lower in the tree. Right? This is really the only thing that we'll focus. And of course, we can formalize this, and that's the definition that we had before. But let me highlight perhaps the key properties in here. The key properties are that when you look at the variables that appear in every node, the only variables that appear in one of these things are all the variables that are in the corresponding maximal clique. So 7 will only contain variables 7, 8, and 9. 6 will only contain variables below on the tree. Right? So there's a nice structure in here, in there. And that's exactly what the definition formalizes. Again, let me perhaps highlight the important things. A chordal network is a directed graph. Nodes are polynomial sets. I told you this. What's important, every node is given a rank, that this number. And what's important is that the variables that appear in the corresponding node, they're only the variables in the clique corresponding to that rank. And furthermore, it's tree-like. There's arrows, and they go from a parent to a child in the elimination tree. Again, I think a picture is worth more than the definition, I think, for the purpose of this talk. Right? And what I want you to notice in here is that what's going to happen is very much the same thing that happened in the coloring example. This is a data structure that's encoding all the solutions of my polynomial system, because I can play exactly the same game. I can start at the end. I can compute the solution of this. And I can move in here, compute the solution of this. And as long as I compute the spanning tree of this, I'm going to be able to produce a solution. And it turns out that there's going to be a one-to-one correspondence, in this case, between all the subtrees that we want in here and all the solutions that we want. And the really important property, of course, is that this may have exponentially many subtrees, even though this data structure may be very compact in there. Right? How do you compute it? Let me again, perhaps show pictures. But the idea is that when you start with the polynomial system, there's going to be an iterative process, very much like the chordal elimination that I described before, that's going to take my system, it's going to do some operations on it, and it's going to produce a chordal network at the end. So if you want to see pictures, it may look like this. From my initial system, I can, in a very straightforward way, write a very simple path description in there, where somehow it's obvious what do I assign to each level. And then I run a sequence of operations or simplifications. So in here, for instance, I will take this, I will decompose it into nodes. It turns out that then I can move some things lower. I mean, there's a finite sequence of operations that I can do that, kind of slowly, it will get me to the final object in here. If you've ever seen, essentially any algorithm, kind of it's exactly the same thing. In here, there's a sequence of operations, triangulation, elimination, and merging, that if you apply them one after the other, it's going to reach a fixed point, and that fixed point is going to be this chordal network in the end. There's a way of computing that, and under the right conditions, this is going to be polynomial time. Now, how do we use it? Why this is important, or why we like this a lot? Because given a chordal network, there's a whole bunch of problems that you may ask that are going to be able to solve in linear time. If you want to count solutions, counting all the possible paths, counting all the possible, the cardinality of my variety, the cardinality of the solution set, there's going to be a nice recursion that's going to allow you to count the number of solutions. If you want to compute the dimension of the variety, again, in the examples that I described, you have finitely many solutions, but the same thing is true if you have components of higher dimensions. And in particular, there's very nice, clever algorithms. I'll describe an example, for instance, for solving the ideal membership problem. Essentially, you want to know if a polynomial vanishes on the feasible set or not, to compute the equidimensional components. I mean, lots of questions that you would like to ask about the polynomial system. Kind of, once you have a compact representation of this type, then you can solve this. And given the time, I think I'd rather have time for questions. Let me not describe. It's a very clever algorithm. Diego wrote this wonderful algorithm to do this. I feel guilty for not discussing it, but I'd rather have time for questions. So let me just mention a couple of things. I have just a couple of slides to go. First of all, there's very, very interesting connections. We didn't realize this at the beginning. There's some very, very nice connections with some data structures that people have used in computer science. If any of you know about something called a binary decision diagram. So a binary decision diagram is a very clever representation of a Boolean function. So if you want to represent a Boolean function, you have binary variables, and you have a binary function, there's a very nice data structure, which essentially corresponds to some kind of branched decision process, or a read once program, where you could read variables at a time, and one at a time, you never backtrack, and based on their order, you may jump ahead and produce a value of the functions. Again, what's interesting about this is a couple of things. So first of all, I guess there's this notion that somehow it's really one of the only fundamental data structures that have appeared in the recent 25 years. At least Don Knuth wrote this in the fourth volume of the Art of Computer Programming. But perhaps more important, of course, is that this actually made the development of this BDDs actually in Berkeley, this enabled lots of very significant advances in formal verification and model checking. It's not just like a theoretical construct, but actually you can do lots of very practical and very efficient things. And one thing that we're kind of surprised that in a very particular situation, when you look at equations, something called monomial ideals, essentially our chordal networks will reduce to this case, but in the general case, you can do a lot more things than what you can do with BDDs. And I guess we'll explore a little bit more that in the future. The only thing that I want to show you in terms of, we've implemented this in both in finite fields and in general, and the only thing that, for different problems, and I just want to show one example, because really the only thing that matters in here is that why you can do things that somehow no other method could do unless you exploit this structure. The example doesn't matter, it's something that comes from something called vector addition systems. It's really about trying to understand, in this case, where this polynomial vanishes in the solution set of these equations. Again, the details don't matter. We're comparing this for different values of n. N in here is the number of variables with some other state-of-the-art methods in solving polynomial equations. And the only point that I want to mention in here is that what you can see is a difference between our algorithm. These are timings for our algorithm versus the other ones. Is that you can see very clearly, again, numbers don't really matter, the exponential behavior that these two other methods will have, that as a function of the number of variables, they're going to be growing exponentially. So regardless of how clever these other methods are, because they don't exploit this kind of chordal structure, they're constrained to grow exponentially. And in here, because we realize that somehow this system has small tree width and we do things in the right way, what you get is a growth that's linear in the number of variables. So we can do this all the way to 1,000 variables, and really there's not really a problem, but these methods very, very quickly run out of steam. So of course, this is not a general recipe or a miracle. You really have to have problems with the right structure. But the point is, whenever you have problems with the right structure, and we didn't make this up, I mean, this came from some other paper, then you really have huge differences. Summary: this graphical, hypergraphical structure may simplify optimization, solving pretty much any task that you may want to do. You need conditions. Tree width is not enough, particularly for continuous problems. You have to be careful, somehow that these algebraic geometric conditions or something equivalent, they're somehow satisfied if your problem is not discrete. And if you want to know more, some references, and that's it. Thank you for your attention.
Questions? Yes, John.
So in the case where the field is algebraically closed and it's an infeasible system, you expect a dual certificate, a dual Stellensatz certificate. If you have a polynomial system that's infeasible and the field is algebraically closed, you expect a dual certificate of infeasibility.
Yes, but that could be,
No, so I'm wondering, in these cases where you're bound to tree width, can you get that certificate more easily?
So you can get this. You can get certificates. So think about again the case of this knapsack, this version of knapsack, right? If you write them in the obvious, the obvious certificates, they will still have large degree. Because really, the only thing that I've done is apply some kind of linear transformation on the variables. What happens? What really these things are giving you are structural certificates. So you can use this, think about, I guess, a coloring example, right? You can use this to write a particular certificate where you write the polynomials, think about in the Null-Stellensatz case, not in dense form, but you write like an evaluation expression for this. You write a straight line program that will compute those certificates. And those are small, just like in here you have a small description, but if you were to expand it out, then you would have this huge polynomial.
Yes.
So you're talking about Grobner basis. Does the moment matrix come in at all? Can you do that instead of the Grobner basis?
Not really. I think somehow there's... no, the answer is not really. And again, the example is exactly the same thing of the knapsack examples. Right, even in there, even though, for instance, your set of equations has a structure of a path, a very simple structure, you won't necessarily have certificates of low degree. So it's not that you can guarantee that these semi-definite relaxations, at least the obvious ones, they're going to work in small degree. There may be in particular situations, again, like the 0-1 case, ways of bounding the degree. In the 0-1 case, for instance, exactly the same result will happen. In the 0-1 case, there are results. Bienstock and Wainwright and Jordan, and Monique Laurent has results of this type. That if you have 0-1 problems, then you can bound the degree of these relaxations in terms of tree width.
But you need to find the ideal. You can't use the moment matrix to help you find.
No, you don't need to do this. That case, if you just write the standard relaxation, and the point is you just show that it ends. At some point. So you don't really, I think in that case, you don't really see the difference.
Yes.
I'm not an expert on system of polynomials, but I'll give an introduction first. I worked on solving complex polynomials for a long time through iterative methods. And as you know, one of the important things in that approach is to compute bounds on the modulus of zeros. In fact, a few years ago, I had an REU student in summertime, and he knew about system of polynomials, so we tried this cyclic coordinate method using iterative methods to solve some baby systems. The question that I have is, are there any bounds on the modulus of system of polynomials that can be computed?
So you want bounds on, I mean, there are bounds. I mean, there are known bounds on, you know, kind of somehow, if you give me a system of equations, every root, you know, kind of will have to be less than.
In terms of, say, coefficients, because for complex polynomials, for instance, you can compute very good bounds on the modulus of polynomials. In fact, asymptotically, you can give the optimal bits. So I'm just curious, from, if nothing else, maybe theoretical point of view, is there a way to look at the system of polynomial equations and its coefficients and cook up a bound up or down?
I mean, there are bounds of this type. Typically, what you do is you do elimination, right? Like, you know, kind of, you could take this system of equations and, like, you know, kind of boil it down to the univariate case, and then you would use bounds on the univariate case. I mean, there are things of that flavor, and, like, you know, there are also techniques based on, like, you know, convex optimization that will allow you to, like, you know, put a ball around the solution set. I mean, there are a number of things that one can do. Yeah. I can give you some pointers if you want.
Yes.
So there are many other notions of width, like this clique width,
Yeah.
branch width. Does any of that give you extra?
That's a good question. I don't know. I mean, likely the answer is yes, you know, kind of, but I don't quite know, you know, kind of. Somehow, one of the things that I think we like about tree width is that it's somewhat canonical. I think you know, I think as you start going into more, you know, kind of all of those ones, it starts becoming a little bit less obvious, you know, kind of how transferable
Like
it
in
is.
this Corcel setting, it gives you more power to look at.
Right, branch width. Yeah. I mean, like, yeah, no, that's absolutely true. I mean, there's classes which are not like, I mean, so certainly that theorem doesn't have a converse, right? It does not imply that, you know, kind of that you cannot solve problems on certain other families, even if a tree width is unbounded in polynomial time. And some of those refine this in a better way. But we don't know to what extent. I mean, part of the thing is that, you know, there's at least 5 different ones. I think probably the most canonical one, the one that you know, kind of we were planning on doing something is this hypertree width, right? That, you know, kind of they try to look, not that somehow not do this brutal abstraction that we do of going from the polynomial system into a graph, but, you know, kind of retain a little bit more information, and you know, the hypergraph in there will allow you to do a little bit more. And I think, at least from what we were reading, you know, the nicest generalization in that setting is hypertree width. But, you know, kind of, we don't know to what extent this will work. I mean, likely something can be done, but we haven't done.
So suppose that I have a class of distance geometry problem instances, okay, for which somebody can provide me with some such data structure, okay? I don't know how to construct it, it doesn't matter. Maybe they're not even chordal, but these things can be given, okay? Magically, by God. So it's a certificate. If it could be used both to construct like a, you know, an infeasibility proof, if the instance is infeasible, and to compute any type of solution to desired accuracy, because it's an algebraic definition and finite definition, if the instance is feasible, then that would mean that that class of instances is actually inside NP, which is not clear right now for distance geometry problems.
I mean, one thing that you can get is, and for instance, and I mean, there's other older results, but, you know, Dan Binstock, for instance, has a paper on, you know, how you can produce approximate solutions in a very particular sense, you know, kind of whenever you have bounded tree width. I mean, regardless of, you know, variables being continuous on discrete. It's really a discretization argument. And, you know, kind of think about, again, this knapsack example, right? You know,
I'm saying that this could be the solution itself. Could I define this to be the solution of a system of polynomials? If I can construct, if the system polynomial is infeasible, and I can easily construct a certificate, and if it's feasible, I can easily, you know, verify that it's feasible.
I mean, what I worry about is, again, in these very simple cases of the cycle, right, like on realizability in one dimension, you're immediately into knapsack.
No, I agree that this is not a solution. So, but I'm saying if this could be treated as a certificate, like to say that a certain class of polynomial equations could be inside of the class NP and not just maybe NP hard?
I mean, then I would not really think about, I would think about things like semi-definite relaxations, right? I mean, in which case you have classes of instances that you can certify efficiently, like, you know, kind of sometimes with structural certificates of different kinds. But like, you know, I think the goal in here is a bit different. Like, you know, and I think in there, somehow if you give up completeness, if you don't care about, like, you know, kind of producing solutions for in every possible instance, then there's somehow more efficient things that you can do. Like, you know, kind of disproving solutions, like, you know, there's cheaper ways of doing it.
Yes.
So you mentioned Perl and belief propagation a few times. So belief propagation is defined over acyclic graphs to be an exact inference method. But loopy belief propagation is actually shown to converge exactly in special cases of graph structure.
So essentially what you do in graphs with cycles, you construct these click trees, right? So you construct another graph where the nodes are subsets of the original ones, and that other tree is acyclic. And in that case, you have exact,
Then just a generalization of that.
I mean, I mean, again, once it depends on what in your mind is belief propagation. I mean, if belief propagation is like, or like, you know, dynamic programming, if it's a general philosophy, it's kind of the same thing. Like, you know, kind of if it's a very specific flavor of it, then like, you know, kind of, yeah, it's different. So, I mean, there are versions if you want, like, you know, kind of. I mean, I'm not talking about this part, right? I mean, this is genuinely new. I'm saying, like, you know, kind of for these kind of algorithms that we're talking about. I mean, really, there's no distinction between belief propagation or like, you know, these non-serial versions of dynamic programming. And the question of, like, you know, cycles or non-cycles. I mean, once you go to these chordal completions, like, you know, what you do is you do dynamic programming not on the original graph, but you construct this other click tree where the nodes are now clicks, and that graph is now acyclic, even though the original graph has cycles.
Right, but there are graphs on which belief propagation is still convergent.
You're saying the standard version of belief propagation when you do node-based, yeah, sure, yeah. No, this says nothing about that situation. Yeah, and that's actually the case that, I mean, even in the simplest possible settings, we don't understand what. You know, and I think there's, I mean, walk-summable families. I mean, there's families of graphs for which, you know, kind of we understand, but I don't think there's a theory. I mean, of, you know, kind of the acyclic cases where belief propagation works.
Okay, thank you very much.